casual, but we are recording. Hey, what's up, all our poll workers? It's election day, and you guys are out sitting in the cold, keeping democracy happening. Thank you for your service and sacrifice. I think you guys can see me, but you can't see everybody else. I don't know exactly how it works. So, but we're all here cheering for you, and stay safe out there. Anyways, we're recording this so that you can not miss out on a fascinating talk about sex-linked traits. I'm sure you guys are really sad right now. Okay, so let me share a screen. I got to reshare that. Here we go. Wait, screen 2. Okay. All right. Can you guys see the screen okay with the karyotype? Yeah. Okay. So this is a picture of a karyotype, and what was I saying? Shoot, this is recording. There's so much pressure. So we got 46 chromosomes here, and you guys know you get 2 from every parent. Okay, yeah. When you get nervous, just start repeating things that you like know for sure. So I know for sure there are 46 chromosomes. You get 23 from each parent. Now, the important thing that we want to point out here is that in these chromosomes numbers 1 through 22, okay, all of these are referred to as autosomal chromosomes. I've mentioned this before, but I just want to reemphasize that. Autosomal chromosomes, which are always, in pairs, right? You get one from your mom and one from your dad. These are chromosomes, and on those chromosomes, you have genes that are found in both genders. Okay, and so it doesn't matter if you're looking at a man's karyotype or a woman's karyotype. When you look at chromosomes 1 through 22, there's nothing gender specific about it. Okay, and so something to jot down and note here is that if you have traits, okay, when we're talking about inheritance, if you have a certain trait or a character that is labeled autosomal, that means that it's going to affect males and females equally. Okay, so for example, your eye color, not to be confused with color blindness, which we're going to talk about today, but your eye color is a autosomal trait, right? So when we worked with the problems in the homework the other night, where you had brown eyes are dominant to blue eyes, okay, whether you're a male or female, when we wrote out genotypes, we could write them out like this. Here's an example, right, where mom and dad are both heterozygous. Both of them would have a B. Okay, it could be homozygous dominant, heterozygous, or homozygous recessive. But the point is, both parents have 2 copies of the alleles. Okay, and so there's nothing, and then when you make the Punnett square, I'm not going to do it, but when you make the Punnett square, there's nothing specific to say that boys or girls have a higher chance of getting brown eyes versus blue eyes, because that's what it means to be autosomal. Okay, now in contrast to that, what we have in the bottom corner is the 23rd chromosome, and this particular picture shows X and Y. Chromosome 23. You still have 2 of them, one from each parent, but these are referred to as your sex chromosomes. Okay, and these are specific. Now, if I zoom in on it, I'm going to draw a picture here. One chromosome in humans is the bigger one, and this is the X chromosome. Okay, and the X chromosome stores a lot of really important genes. Remember, we refer to these as gene loci, but the gene loci on the X chromosome have really critical genes that are important to every person, whether you're male or female. Okay, and so all of us have to have at least one X chromosome. In fact, if we are missing an X chromosome, usually the zygote is not viable. It's not going to survive because it's missing, thousands of really important genes on the X chromosome. Okay, now the other possible chromosome we could get, okay, normally like if it was chromosome 1, you have chromosome 1 from mom, 1 from dad. You have 2 copies of the same homologous chromosome. But in the sex chromosome, you can have an X, and obviously that you could have 2 X's, which makes you a female, right? So all the ladies in here, you have an X from your mom and an X from your dad. The guys in here have an X from our mom, not our dad, and we'll talk about why that is in a sec. And then the other chromosome is a shorter one, a stubby one called the Y chromosome. And the important thing to note here is that the Y chromosome is not, in mitosis and meiosis, we would refer to them as homologous chromosomes because they have the same number. But what you need to know is that the genes found in the Y chromosome are completely different from the genes found on the X chromosome. It's a completely different set of genes, okay? And these genes are not essential for a human to develop, okay? Because ladies don't have a Y chromosome, and yet they develop perfectly, right? So the Y chromosome is kind of like an extra set of genes that, and we're going to talk about some of those genes in the podcast today, that determine the gender. Okay. And really what it is, it's not, it's not that the Y chromosome determines your gender, because the ladies have a gender despite not having a Y chromosome. What it is that the Y chromosome is what switches on. If we turn on those genes, it's what causes one person to develop as a male. Okay. If you didn't already know this is kind of some fun trivia, and you could jot this down if you want. All of us start off developing as a female. Okay. When you're early on in development, our cells and that embryo that's developing is mainly just focusing on using the information from the X chromosome as well as the 22 autosomal chromosomes to grow the human being. Okay. And all of us started developing as a female. But at some point, the Y chromosome, if we have it, gets turned on. And the genes, like the SRY gene on the Y chromosome, turn on. And that's what triggers a shift from female characteristics towards male characteristics. And that's why, guys have different features. Okay. Now, as we're going to point out that in the period here, it's not as black and white as they used to think, because the expression of think about this, if what makes you a male is not even the fact that you have a Y chromosome, it's the fact that these genes have to be turned on, then, it's not as simple as people say, where like, oh, well, XX is female and XY is male. It also involves the expression of these genes and how those genes are expressed and which versions of those genes you inherited. Right. And so it brings about a lot of really interesting ideas when we think about topics of gender and sexuality, and a lot of conversations about breaking out of this like gender binary system where you're either male or female, because the reality is that, like, even on a biological level in the natural world, things are not that black and white. And we'll look at some examples of that later on. Okay. So that's the first thing I want to point out, is that is kind of the division of your genome between autosomal chromosomes and your sex chromosomes. Okay. And obviously we'll just kind of go in the simplest form here. You guys should know that generally speaking, if you have 2 copies of the X chromosome, then you are going to be a female. And if you have an XY chromosome, you are going to be a male. Right. And that's why I mentioned earlier, guys, our X chromosome has to come from our mom. Why is that? Because you had to get your Y chromosome from your dad, right? If you think about this from a meiosis perspective, and actually for this, I'm going to switch over to a whiteboard just so I have a little more room to draw and write and all that stuff. If you think about this from a meiosis perspective, I want you to take these chromosomes and place them in gametes the same way that we would place them, if we were working with autosomal chromosomes. Okay, so here's what I mean as an example. Let's say we're doing eye color over here, just to have a kind of side-by-side comparison. Okay, eye color is autosomal. I'm going to put auto up here, which means if somebody is big B, little b, what that means is on their chromosomes, right? Let's say it's chromosome 1 from mom, 1 from dad. One of their alleles is dominant, one of their alleles is recessive, right? And if you cross that with an individual that's homozygous recessive, that means on their 2 chromosomes, at that same location, the allele there is the recessive allele. Okay, but for sex-linked stuff, it's trickier because women do have 2 X chromosomes. Okay, but men only have 1 X chromosome and 1 Y chromosome. And for most of the examples that we're going to look at, unless I explicitly tell you, when we talk about sex-linked traits, we're talking about traits that are stored on the X chromosome. Okay, there are traits, there are disorders or whatever that are found on the Y chromosome, but we're not really going to pay attention to those. We're mainly going to look at genes that are stored on the X chromosome. Okay, so when you look at it from a chromosomal perspective, meiosis is going to happen really in a different way, because let's say that, and going back to the eye color here, right? This individual here, when they go through meiosis, what this means for the heterozygote individual is that half their gametes, if this is the sperm, are going to have 1 big B and 1 little b, right? And the same idea would happen over here if, let's say, for the female, and we're going to notice how we write this, okay? For color blindness, we're going to use a big C, little c. If you're a woman and you're heterozygous, when you go through meiosis, it's going to behave the same way that we see autosomal chromosomes behave, right? Which is that half the eggs are going to have the 1 version of the allele, half the eggs are going to have a different version of the allele. And you notice that I do the X superscript thing. You'll see why. I'm going to explain why we do that in just a sec. Okay, like why don't we just write big C, little c? I'll explain in a bit. On the male side, though, this is where things become different, right? If this is the X chromosome you got from your mom and this is the Y chromosome you got from your dad, when meiosis happens, it's going to separate homologous chromosomes, just like we've talked about. And what this means is that in the male, half the sperm are going to have the X chromosome and half of them are going to have the Y chromosome, right? And that's why human populations generally are about 50% male and 50% female, right? Because any sperm that has the X is going to lead to a girl, and any sperm that has the Y is going to lead to a boy. So it's a 50-50 chance, and it is kind of up to the sperm to decide that, right? But here's the point I'm trying to get at. If this gene, let's say color blindness, is stored on the X chromosome, okay, and by the way, I'll just clarify, normal vision is dominant to colorblind vision, okay? Let's say that this man is normal visioned, X big C. Okay, notice that unlike the woman, he only has one copy of the color blindness gene because he only has one X. Okay, and this, I want to point out, this is why sex-linked disorders affect men more than they affect women. Okay, it's because women have two X's, so they kind of have a backup, right? If Victoria inherits a colorblind gene, right, from one of her parents, as long as her other X chromosome is a normal vision, she's not going to be colorblind. Right? But guys only have one X chromosome. The Y does not have the ability to dominate or balance out or overpower what's happening on the X chromosome. So for guys, whatever X chromosome you got from your mom, that's going to determine your phenotype. Okay. And so this is what's different about sex-linked traits versus autosomal traits. Okay, is that in autosomal, the way you write out and do inheritance in autosomal chromosomes is very straightforward, right? You just take the homologous chromosomes and you separate them, and you don't have to account for gender at all. But when we do sex-linked stuff, we have to write it out as in this XX and XY system. Okay, here's what I mean by that. Remember I told you that we have to use this X superscript system? Here's the reason why, okay? I'm gonna do it wrong over here on the side. Let's say I want to talk about color blindness, and I say, hey, normal vision is dominant to color blindness, okay? And we say a woman is heterozygous for color blindness, and then the man is normal vision. If we use just this normal system without the X's and Y's, this is how we would write out a autosomal trait, right? Is that both parents have two alleles. But what's wrong with this? Can the man have two C's? No, right? Why can't the man have two C's? Because the colorblind gene is stored on the X chromosome. And how many X chromosomes does every guy have? Only one, right? So if you write sex-linked traits out like you would write a autosomal trait by giving both parents two alleles, you can do it and you can make your Punnett square, but your probabilities and your outcomes are going to be completely wrong. Okay, because the way that sex-linked traits are inherited is very different because of what's happening on the male side. Okay, so let's go ahead and draw this out and see what would the Punnett square look like if we were doing a sex-linked cross. Okay, so the woman is heterozygous. Okay, we also call her a carrier. Maybe you want to mention, make a note of that in your notes. Okay, a carrier is a person that carries the recessive allele but does not actually show the recessive phenotype because they're heterozygous. So carriers are essentially heterozygous. Okay, can men be carriers? What do you guys think? Can a male be a carrier? Answer is no, right? Because he only has one copy of the X gene. Okay, so when we make our Punnett square, here's how we're going to do this. Sorry, it's a little messy. We're going to put our sperm on the top and our eggs on the side. Okay. And notice X and Y are in different sperm, right? Just like the two X's from the mom are in different eggs. When we put these two together, we're going to go ahead and put the X's together like this. This is a big C from one parent, big C from the other. This one's going to be a big C from one parent, little c from the other. Same rules apply here. The dominant, if there's two of them, if they're heterozygous, the dominant one always goes first. Okay. And then on the male side, X is always going to go first and then the Y. Okay, so we have the X big CY and then we have the X little cy. All right. So what is the difference then between sex-linked and non-sex-linked characters? Well, if we were to do it this way, right, with the green font with the big C's up here, without even doing the Punnett square, we would know that 100% of the offspring here would have normal vision, right? If we cross a heterozygous with a homozygous recessive, all of them would be normal, right? And it wouldn't affect one gender more than the other. However, because it's sex-linked and because the guys only have one copy of the X allele, right, or the X chromosome and the allele that's carried on the X chromosome, look what happens here. In this cross here, we differentiate first by gender, right? Let's go by it with the women here. Of the daughters here, how many of them are colorblind? None of them, right? Both of them have at least one dominant allele, and that's enough to keep them both, give them both normal vision, right? The normal phenotype. So 0% of the daughters are going to be colorblind. On the guy's side, what's the probability of being colorblind? It's 50%, right? This son here is going to be fine because he's getting a dominant C from his mother, but this son here is getting a recessive C from the mom, right? And because he doesn't have another X to balance it out, he has that Y, whatever he gets from that mom is automatically going to determine his phenotype, which in this case makes him colorblind, right? So you can see there's a 0 chance of the daughters being colorblind, but a 50% chance of the sons being colorblind. Okay, and this is a big indicator. If you're asking yourself like, hey, is this trait or this disorder, is it sex-linked or not? The key thing you're going to look at is, does it affect the boys more than it affects the girls? Okay, if the answer is yes, then that tells you that it's most likely going to be sex-linked. Okay, now what would a problem look like, you know, that comes up with that? I mean, obviously I could give you the genotypes and ask you to do the cross, and that would be an easy genetics problem, right? But a trickier genetics problem, kind of like what you guys did in the homework the other night, is oftentimes we give you the kids and then we ask you what the parents are, right? And that's the new thing that we're going to add to this, is that whenever you get a genetics problem, you look at the kids, right? You might get data that looks like this. You might see okay, normal visioned girl. You might have a colorblind girl. Okay, you have normal visioned males, and you have colorblind males. And what it's asking is how many of all of these are there? Okay. Now here's the example. Let's say that out of a population, you get 10 for all of these. Based on the data here, does it appear that colorblindness is autosomal or sex-linked? Based on the numbers that I gave you here. Keep in mind, the girls have the same distribution of normal and colorblind as the guys, right? So if that were the case, is this going to be autosomal or is it going to be sex-linked? The answer is it's going to be more autosomal, because it affects the genders equally. Okay, but if you see that normal visioned females are 20, colorblind females are 0, normal visioned boys are 10, and colorblind boys are 10, is it affecting one gender more than the other? Yes, it is. And if you see that, that tells you then that colorblindness is probably sex-linked and found on the X chromosome. Does that make sense? So this is there's kind of like two big things that you got to be careful about. Okay, number one is when you get a data set, you need to be able to look and figure out, is this autosomal or is it sex-linked? Okay, once you determine that it's sex-linked, then when you go to do your Punnett square, the second big mistake that I find people do is they end up writing out their genotypes like this. Okay, we do not do just normal letters if it's sex-linked. If it's sex-linked, you have to use the XX and XY system. Okay, and the easiest way to do that, guys, is just to start out by writing XX for the woman, XY for the male, and then try to figure out what these parent genotypes are. Okay, is it going to be big C, or is it going to be little c, or is it heterozygous? You know, is this one a dominant or is it recessive? You can tweak all those things after, but just by the moment you realize it's sex-linked, if you write XX, XY, and then you are asking yourself, what do I put above these X's? That's going to keep you from making the mistake. Okay, and I just can't emphasize this enough, because I see this all the time on tests. People tell me it's sex-linked, and then they go, and this is the essay prompt part or on the AP test, they say it's sex-linked, and you're right. And then we ask you to do a Punnett square, and then people start writing things like this. Okay, and you can see where that's going to give them completely the wrong results. Does that make sense to everyone? Okay. So I got a question here. What's the difference between gender and sex? It looks like they're both synonyms of one another. Yeah, it's gotten a little bit more complicated these days. Traditionally, I think they in the old days, it kind of meant the same thing. Sex, I think, is more, if we're looking at the more formal definition today, sex is referring to like biologically, what do you well, there's kind of different ways to determine. You can look at it from the XXXY system, or anatomically, you can look at the sex of a baby, right? And look at their genitalia and say, are they male or are they female? Okay. Gender, on the other hand, is more on a spectrum, where it's more about masculinity and femininity, right? And again, in the old days, you basically, like, your gender was either like you're male or you're female, in terms of your like outward characteristics and even like your roles, right? You've heard of people talking about gender roles. So I think I'll have to double check to be sure, but I think if we use the word sex, we're talking about biologically, like anatomically, on a chromosome level. In a gender perspective, it's more about like a societal role that you're playing. So the traditional gender roles of like men and women versus now, like it's a little bit more blurred. Okay, to say that it's not just a binary gender system. So I don't know if that answers your question, but it's a little blurry. Okay, does that make sense to everybody? Just like how sex link stuff works? Yeah. Okay, so here's your homework for tonight. The homework, if you, I'll pull it up here on my screen. Let me switch over to my. So when you download the homework for tonight, it's a 2-page document. Okay, and let me clarify this, or maybe make note of this. You're only doing the first page tonight. Okay, the first page is the sex-linked questions. The second page are the recombinance questions. We're not going to cover this until early next week. Okay, so do not worry about the second page. It's not going to make any sense to you. Just focus on the first page. The first problem is pretty straightforward. It's pretty easy. Okay, it tells you that it's, color blindness is recessive. It's carried on the X chromosome, and then they tell you about the parents, and they're asking you probabilities of the kids. Okay, the second question involves something called a pedigree, and it looks really intimidating, but it's actually quite simple. A pedigree is basically a family tree. The squares are males, the circles are females. Okay, now you'll notice some of the squares, most of these are white. They're not shaded in. A few are shaded in, and a few have dots in them. There's a lot of different ways that people can do it, but they will always tell you like what system they're using. In this particular case, if they're shaded in, that means that they are affected by the trait. Okay, it means that they have this disorder. If they have a dot, that means that they are a carrier. Okay, and I don't want to give away too much because I want you guys to kind of work through it, but I do want you to notice, just by looking at this pedigree here, can you tell if it's sex-linked or not? Right, if shaded means that you're affected, and square is representing the males and circles are the females, you can tell whether or not this is sex-linked, right? So this one here is just, this question here just has you go through, and it's going to have you like predict the genotypes and the disease and all this kind of stuff in this particular family tree. Okay, and this is called a pedigree. The last one is an actual genetics problem from the AP test. It's an essay question, so I wanted to throw that at you guys, but it's gonna, you can read through it on your own, and I'm not gonna give you too much help with it because I want to see you try to figure it out on your own. Okay, and we can definitely go over it on Wednesday, but this first page is your homework for tonight. Okay. All right, so that being said, I'm going to, well, if does anybody have any questions before I stop recording? We're good. Okay. So folks that are listening to the recording, I'm going to stop it here because we're going to move into the podcast. And when I email out the recording video to you guys, I'll include the link to the podcast. We're probably just going to listen to about the first 25 minutes or so of it. Okay, and you can just listen to it, enjoy it, take down some notes about whatever you learn. So I'm going to go ahead and stop recording. And thanks again for working those polls for us.